Hi, my name is Tushar Goel and today I'll be talking about NAND2TETRIS. NAND2TETRIS is building a modern computer, a basic modern computer from the first principle, that is the basic NAND gates. And usually NAND2TETRIS has 12 projects, but I'll be discussing about only 4 projects, that is the 5th, 6th, 7th and 8th in this video. Coming to the 5th project, it's computer architecture. Like in the previous 4 projects, we have built the computer's basic processing and storage devices, that is ALU and RAM. But in this project, we put everything together, yielding the complete hacked hardware platform. Like there are 3 chips in this project, that is memory, CPU, and computer. The memory chip, to describe it, is basically the entire RAM address space, and the CPU chip is the hacked CPU, and the computer chip is the platform's topmost chip. We'll test all these chips by running some hack programs on the constructed chip. Now, coming to, I'll show you the website. So this is project 5, that is computer architecture. Like it's written about the chips of memory, CPU, and computer, and we'll be running different programs and we'll testing different chips. So we use hardware simulator for running the files in project 5. First we load the chip from the First we load memory.html, and then we load the script for memory.html. As you can see, the code is over here. This is the input pins displayed. This is the output when we're getting the output, and this is the internal pins inside the chip. I'll just fast forward the process so it is done fast. We can see that is the code has been run. Now if we look at the output, this is the output, this is the memories, this is the memory we get from the input page on the output page. The value is 0 and the input is 2, 3, 4, 5, 2, 4, 5, 6, 7, 2, 4, 5, 2, 4, 5, 7, 6. Similarly, now I load CPU.html, and then I load CPU.html. Here we can see different instructions written in the code, the value that we're passing, and we have 4 output pins and we have 3 input pins. I run the code. You can see the output from here. You see how at different values we have a reset pin, an address is given, PC value is there, program number is there, and we have a register value. Then I load the computer chip. Now we have different computer programs. I do the computer ITST. Which adds up to 2 constants, 2 and 3, and will write the result in RAM 0. And the code. So we get the value 5 at PP out and do the output from here. Similarly, I'll use computer max.tsc this time. This computes the maximum of RAM 0, RAM 1, and will write the result in RAM 2. When I talk about 0, 1, and 2, I'm talking about the latest position. So here, RAM 2. Let's check the output from here. We have the value 2, 3, 4, 5, 6, 7. Coming to the last script for computer, you will see computer rect.txt. It is basically we're drawing a rectangle with 16 pixels and length RAM 0 at the top left of the screen. the output using this a rectangle with a width of 16 pixels is formed. So this is it for the chapter number 5. Now chapter number 6, we have the assembler. So the assembler program translates program written in the symbolic hacked assembly language into binary code that can execute on the hacked hardware platform built in the previous projects. Looking to the website, there are basically 3 ways to describe the desired behavior of assembler. When loaded into the assembler, program file containing a valid hack assembly language would be translated into a correct hack binary code and stored in program.hack.file. As you can see over here, the about memory CPU is written over here. This is the project. Second is output produced by the assembler will be identical to the output produced by the assembler supplied with the NAND2TETRIS software suite. As you can see, the objective is to write an assembler program that translates program written in symbolic hack assembly language into binary code. So we open the assembler, we load a source file from project 6. As you can see, this is project 6. First I do add.asm. I'll run the add.asm file. It basically adds up to constants 2 and 3 and puts the result in R0. So as you can see, this is 2, this is 3, and it's writing the result in R0. Now I'll load another source file, that is max.asm. Max.asm computes the maximum of our R0 and R1 and puts the result in R2. As you can see, as I go through the code, I get the output for the maximum value. Now if I load the source file of RECT. RECT basically we draw a rectangle at the top left corner of the screen. The rectangle is 16 pixels wide and 9 pixels high. So this is the output we get for the rectangle file. Coming to the last file of the assembler, I'll take it pong.here. So this is a single player Pong game. If a player bounces off the ball, a ball bounces off the screen's ball. The player attempts to hit the ball with a paddle by pressing the left and right arrow keyboard keys. For each successful hit, the player gains 1 point and the paddle shrinks a little to make the game slightly more challenging. If the player misses the ball, the game is over. So this is the code for that game we have made. As you can see, the code is huge. So I'm going to try to run it fast. As you can see, the code is very large and I've already made this part. So as we go through the code, we'll get the output, and at the end we'll get the output of the whole code. That is the ping pong game. So I'll leave it over here. Coming on to our 7th project, that is the VM1, the virtual machine 1 stack arithmetic. So VM translator focusing on the implementation of the VM's language, stack arithmetic and memory access commands. And in project 8, this basic transistor will be extended into a full-scale VM translator. So we'll build a basic VM translator in this module, and we'll write a VM to hack translator conforming to the VM specification given in the module. And depending on the programming language that we use, the VM translator should be input using file name VM translator file.name.vm. We'll be uploading this file in the VM emulator later. Go to load program. First we load basic test.vm. Then I'll load the script for the command basic text vme.txt. This is the whole script for the basic text. So we're handling stack arithmetic. So as you can see, we get the RAM output over here and then we get the global output over here. If you want to see the output, this is for the RAM. We have different addresses over here, RAM addresses. The final stack value is 472. We're running memory access command right now. So the next memory access command is pointer test.vm. I'll load the script as well. All these VM languages push and these are all push and pop commands. We handle the memory segments. You can see the output over here. Final stack value is 6084. Now we'll come to the last command of memory access, that is static test.vm. And put the code over here. Code. This tab is getting updated. And the final stack value we get is 1110. Basically, this was stage 2 of handling memory access commands. First, stage 1 is handling stack arithmetic commands. So we come to stack arithmetic. Let's do a simple add.vm. These are the generic push ladder command. It's a generic push command. The first argument is constant while the second argument is non-negative integer x. This command will come handy at the early stage, and it helps provide values for testing the implementation of arithmetic logical VM command. I'll do this script coming out and then I run it. As you can see, the final stack value over here is 15 and the RAM 0 and RAM 256 values are given over here. So you can see the RAM 256 value is 15. Another one of stack arithmetic commands is your stack test. So let's look for stack test. So we have 11 different RAM sections and the final stack values are given over here. The final one is -91. So we we've done with stack test, we've done with sample add, we've done with memory access, and SRC we don't run for it. So basically we've done with 7 programs. Now as we go to 8th project, that is program control in the VMC. So basically we're extending the basic VM translator that we built in project 7 to a full scale VM translator. In project 7 we focus on handling the stack arithmetic and memory access commands of the VM language. We now turn to the VM language branching and function calling commands. This also will be using through VM emulator. So we'll test the different commands right now. First I'll run a basic loop.vm. It basically computes the sum of 1 plus 2 plus 1 plus 2 plus 3 by 2 n and pushes the result onto the stack. Basic loop.vm. and the script is basically the taste. So we're using go to and if go to commands over here, and the output we get is the final value is 6 in RAM 256. Now loading Fibonacci series program, which computes and stores in memory the first n elements of a Fibonacci series. This is a more challenging test of the VM's branching commands. This means the value is getting updated in the global stack. And these are the different values we get at different parts of the RAM. 0, 1, 1, 2, 3, 5. Now we'll handle call and return commands. So let's go with simple function of the It performs a simple calculation and returns the result. So this is the output we get at different RAM values. Now I'll run different program. Let's run sys.vm. This tests several requirements of a function called protocol. We can't run sys.vm. So we run class2.vm. So we get a final value over here that is -218. Let's see a Fibonacci element. Fibonacci element basically tests the handling of the VM function calling commands. There's a recursive function that returns the nth element of the Fibonacci series that we just ran a while ago. Over here we're using the recursive. The class functions that we ran just now were designed to set and get various static values. And the static test assumes that the VM runs the initializes the VM implementation. So at the end of this Fibonacci element, we can see that we get the value 3 in the stack. So with chapter 8, we have built a full VM translator. So that is it for this video. As I said, I've completed 4 projects, and using these 3 softwares